Okay, so first, I'm Boaz, and I want to thank the organizer for letting me speak here. The work that you'll see today, and I hope to show you only some of the work, not the complicated stuff at least, was done by Shaya Cohen, Alex Zukernik, Guy and myself. And I want to talk about triplet superconductivity in superconductor ferromagnetic contact. And I want to first introduce some concepts or some ideas that are important for us in superconductivity and why nano is so important and the new physics that it gives us. And later I will introduce proximity effect, Andreev's and reflection, triplet, what is a triplet, and only later I will go into the singlet and double and multiple experiments that we perform. Okay, first, why superconductivity? And the answer is clear because you can do many applicative things in terms of application. For example, drive current in power cables and do microelectronics in terahertz and devices with cellular electronics and so on. And this is only the applicative stuff. I'm not mentioning here in terms of science and physics. And I want to show you an example of a film that we grow in our lab. It's a superconducting film. And for example, here we cool it in liquid nitrogen, and then it floats, the property of a superconductor material. It floats above a magnet. It's a very thin film. And you can see that it has very interesting quantum properties. This is not directly related to my talk, but it's a very nice thing to remember about superconductivity and superconducting films. You see, it's very robust, it's floating, it's very unique. And this film is not magnetic. Okay? So, let's continue. What do we know about superconductivity? We know that the elementary particle in superconductors is not electron, but are couples of two electrons, a couple of electrons, which are have some kind of interaction, some kind of field interaction between them. And usually this interaction in type 1 superconductors, in the old superconductors, is through phonon vibration, the lattice vibration. This is a simple cartoon that shows how the lattice contracts after a first electron, and then the second electron feels the attraction or effective attraction. And this immediately gives us a property of the elementary particle, which is that it has a finite size. And this size can be quite large, at least for type 1 superconductors. You can see here, indium, for example, is 300 nanometer, aluminum is 1.5 micron. And this is important to us because we are not able to produce nanostructures, very small, which are smaller than this elementary particle, which gives us a tool to measure this quantum creature, and a tool to measure how this pairing, how this mechanism of superconductivity really works. So this is the motivation and why nano is so important. And the tool that we use is we use transport measurement. We measure the current that flows between a normal metal, or a ferromagnetic metal for that matter, and a superconductor. And the basic mechanism for transport of current into the superconductor is called Andreev's and reflections. And basically what it means is that electron cannot enter by itself into the superconductor. It has to combine with another electron. So you can see in this simple cartoon here, and again, an electron coming towards the superconductor, and an additional hole is reflected back. So you inject one electron, you get double the charge, because another electron is injected as well. So in terms of conductance, you get double the conductance as compared to the normal state. So this is a fingerprint of this mechanism, Andreev's and reflection. And this will be important for our work. If, on the other hand, if you look at a ferromagnetic metal in touch with a superconductor, if this ferromagnet is fully polarized, and assuming for now that the spins of the electron in this pair has to be opposite, and which is reasonable to assume at first place, because you know that the Pauli exclusion principle doesn't want the two electrons having the same spins in the same place. So they would prefer to have opposite spins. They have the least energy. So let's assume that they have opposite spins. Then for a ferromagnetic metal, if it is fully polarized, this mechanism cannot happen. So the electron will be reflected. And we would not see an enhancement in the conductivity of the junction, the conductivity of electrons entering the superconductor. And this effect was used to measure the polarization of various ferromagnets in this very nice experiment by Solon. Now, I mentioned spin opposite electrons, equal spins. It basically goes down to the question of singlet triplet for physicists. And basically what it means is the singlet state, or the opposite spin case, as you probably, it's more logical to assume that this is mostly the case because of the Pauli exclusion principle, this is the lowest energy solution. However, this solution is very susceptible to magnetic fields, because if you apply a field, the magnetic field will want to turn the spins of the electrons, and it will destroy superconductivity. And the fact is that most superconductors, or almost all superconductors that we know today, are singlet type. It means that the elementary particle has opposite spins. But the triplet superconductivity exists as an option. And if it really exists, it will have, or it can have, if you look at the two components that have an equal spins, it can have a finite magnetization. And in fact, this finite magnetization was measured a few years ago by Kapitulnik and Palevsky. They measured the finite magnetization of superconducting lead, only below the critical temperature of lead, which means that the superconductor has magnetization, which can only be if we have triplet pairing, equal spins triplet. Okay? From now on, when I mention triplet pairing, I mean the equal spin components. Okay? This is what is important for our talk. Now, another concept that is important for our work is the proximity effect. And this is a very simple effect. When you put together a normal metal or a ferromagnetic metal with a superconductor, there are transfer of Cooper pairs from the superconductor into the normal metal and vice versa. Normal electrons penetrate into the superconductor. And for example, here in an article 40 years ago by Guy Deutscher, they measured a sandwich of two ferromagnets and a superconductor in between. And the normal electron, because they are polarized, they destroy the superconductivity slightly, and they show that there is a difference between the anti-parallel configuration and the parallel configuration because of the normal electrons, which are polarized, which penetrate into the superconductor. They show the TC of the anti-parallel state is higher than the TC of the parallel state. So the concept of proximity is very important. Now, if we look at the triplet superconductivity, because the Cooper pairs are polarized, they don't care about the field, the magnetic field. They can penetrate long distance into the ferromagnet. And this fact was verified in an experiment. Here in a very nice example, published in Nature, they measured supercurrent long distances into the ferromagnet, which can only be true if we have triplet pairing, equal spins. Now, so far I introduced you with Andreev-Sanjam's reflection, normal proximity effect, and long-range proximity effect due to the equal spins in the superconductor. Now, as I mentioned, the long-range penetration inside the ferromagnet was measured and is known. But theoretically, it also predicted that this triplet pairing should extend a long range or at some range inside a superconductor. Specifically, we expect the triplet and the singlet can coexist. At some point, at some place, We don't know that yet. So this is the question that we want to try to answer. And another property of the triplet comes from the anti-symmetric nature of this whole superconductor, because the superconductivity is quantum phenomena, and the wave function has to be, the wave function of the electron has to be antisymmetric, and this immediately dictates that the momentum function of the Cooper pairs is antisymmetric. Basically what it means is that electrons at different directions will feel different energy gaps, different attraction between them. There should be some directions when electron will not feel this attraction between them, and superconductivity will be zero, effectively. So, and why do we care about it? A lot. We care about it a lot because it should affect the transport properties. For example, here on the right you see measurements of a material called strontium ruthenate, which is a known P-wave superconductor. And for example, if you inject electrons from that direction, you measure some kind of profile of the conductance. In this case, it's a zero bias conductance peak. This is resistance, but you see enhancement in the conductance, never mind why. And if you come from a different direction, you see what we call a V-shaped cast. This is a resistance, so 1 over the resistance is the conductance. You see a V-shape. And this can be used as a tool to identify the symmetry of the order parameter and the kind of pairing in the superconductor. So let's go down to our experiments. I will introduce 3 experiments very briefly. Single junction conductance between superconductor and ferromagnetic, single junction, double junction, and multiple junction. Now, the first is a very simple cross geometry, which basically means that we inject electrons from ferromagnetic, in this example it's cobalt. You see the vertical line, it's cobalt connected with a superconducting indium. And we measure the conductance of the junction. Now, these are 2, sorry for the scary data, but these are conductance, typical conductance measurement, in which you see the conductance as a function of the energy, of the voltage of the electrons. And at high energies, you see that the conductance is flat. You destroy superconductivity at high electron energies, and you break superconductivity and you go back to the normal conductance. And at low energies, you see some kind of a peak, which is the Andreev reflection peak, or the enhancement in the conductance due to the double electron that you transferred. But what is interesting in our contacts is the V-shape in the middle. And the V-shape in the middle is a fingerprint of an anisotropic order parameter, or something special about the superconductivity in the indium. And I want to remind you that we are measuring indium. Indium is a type 1 superconductor. It is ordinary in all matters. It has very isotropic order parameter, but not here. Here, when you put it in contact with cobalt, you see it has anisotropic nature. Maybe it's a triplet, maybe it's something else. We don't know yet. And this is a comparison with a known anisotropic or superconductor. In this case, it's BISCO. It's a high-C superconductor. And this is a similar cast. Now, we can do also mathematics and fit the conductance with theory, and it works. Now, so far I showed you that the order parameter at the contact is anisotropic. But is it singlet, a triplet, and does it extend inside the superconductor? We have to find it out. So I want to introduce to another mechanism, another tool, and this is the cross Andreev reflection. It's very similar to the Andreev reflection that I showed you before, where 2 electrons join to create a Cooper pair. Only this time, the electrons originate from different metallic leads. Imagine 2 metallic leads close by, and by close by I mean that they are closer than the size of the Cooper pairs. Now, if the ferromagnet is fully polarized, then 1 electron can come if the polarization of the ferromagnetic lead is suitable, then one electron can originate from one lead, and the second one will originate from the second one. And why is it so? And why is it a tool for us? It's very simple. Let's consider two cases. First, a singlet, where the Cooper pair has opposite spins. Then, if we assume that the ferromagnet is fully polarized, which means that there are only spin-up electrons, then in the upper case, the cross-Andreev reflection cannot take place. It can only take place if the ferromagnetic leads are anti-parallel to each other. And vice versa in the triplet state. If the pairing is of equal spins, only in the parallel state the cross-Andreev can take place. So this can be used as a tool to measure the type of pairing inside the superconductor. And for that, what we do is we fabricate two junctions close by. This is indium, vertical indium, connected by two horizontal cobalt wires. And the cobalt wires have different aspect ratios, so we can manipulate them. Different aspect ratios mean they have different switching fields, because we want to switch them to this direction and to that direction. So we can tune the system into parallel configuration and anti-parallel configuration. And now we can calculate all the conducting matrix. It doesn't matter, but basically in that geometry we have two mechanisms to conduct non-locally. Non-locally, I mean from one ferromagnetic lead to the other. The first is just tunneling. You remember we are in the quantum limit. So electron can tunnel from one ferromagnetic lead to the other without creating a Cooper pair. And this is an effect that we don't want, but it can happen. And the second effect is the cross-Andreev reflection, which is the tool that we want to use. Now, we do all the math, and finally we get to the measurement. And I'm showing here three graphs. The green one is the regular local conductance of junction A, which is just, as I showed you before, it has a cusp, is anisotropic, it's reassuring. And the two other graphs, the black and the red one, are the parallel configuration and the anti-parallel configuration, and we want to see which is bigger. And basically what we see is two things. The first is we see that all interesting stuff begins at the conductance peak. The peaks of the green graph is the beginning of all the interesting stuff. The beginning, I mean, at energies below this conductance peaks, interesting stuff happens. And why is that? Because these peaks are roughly the energy gap or the strength of the strength of the interaction between the electron. And once you go at higher energies, you break the electron. So nothing interesting happens at higher energies. Now at low energies, in the middle, you see a distinct difference between the parallel configuration and the anti-parallel configuration. And you see that the parallel state has a higher conductance. So the cross-Andreev is more effective. And basically what it means is that we have a triplet pairing. In a singlet system, this non-local conductance will be opposite. Now, I forgot to mention, but what I'm showing here is the voltage. 2 minutes? Okay, then I'll hurry. We measure the voltage at junction B when we inject the current in junction A. This is a non-local effect which can only happen because the Cooper pair has a finite size. Now, we wanted to simplify things in terms of the analysis, so we came up, or Shai came up with a multiple geometry which looks much, much more complicated, but it turns out that it has an advantage in that we are sensitive in this geometry only to the cross-Andreev term, only to the tool that we want to use. And it turns out that if you see here the resistance, you see a difference only below TC. You see a difference between the parallel and anti-parallel configuration. Again, the parallel configuration is preferred. It has a lower resistance. And we verified that this is really a magnetic phenomena. You see the two states happen only at anti-parallel configuration and happen only below TC. So this is not purely magnetic. It has superconducting origin, these two states. And is it really due to Andreev reflections? The answer is yes. We measure the conductance or the resistance as a function of energy, and we see this effect only below the energy gap, at low enough energies. At high energies, this effect disappears, which basically means that this is due to the Andreev mechanism. Now, this is almost the final slide. What I showed you is, this is actually a summary. I showed you that at a parallel configuration, a triplet order parameter is created, and it extends inside a superconductor what we call a long range. Basically, it's at least 1 or 200 nanometer, which is quite large in these systems. And this triplet mechanism is destroyed when you go into the anti-parallel configuration, because each triplet is polarized to the opposite direction. So the triplet component collide. You can think of as a collision, and this mechanism is non-effective in the anti-parallel configuration. So do I have time to summarize? So I have. So I showed you that the order parameter of indium and cobalt is anisotropic. I showed you that we measured non-local conductance. By the way, it's the first time that anyone was able to measure non-local conductance with and show that it's really due to Andreev reflection, to the energy spectroscopy in this conductance. And I showed you a multiple geometry that allow us to really distinguish between non-local effects. And the bottom line is that there is a long-range order triplet order parameter inside S. Thank you.
Thank you for the heroic metaphor. Triplets of the activities and
Desperate or heroic? It's all clear. It's okay.